Good morning. Welcome back. And we're now getting into the last leg of the respiratory system. Today, we're going to be dealing with the second half of the physiology. And we will deal with, first of all, the first part, the transport of respiratory gases by the blood. So pretty much molecular oxygen, the air, coming from the air that we breathe, is carried in the blood in two ways. A very, very small amount of it, about 1.5%, is dissolved in the plasma, and 98.5% is loosely bound to each iron that is inside the heme of the hemoglobin. And recall that you have four globin chains in your hemoglobin, and these four globin chains carry inside each heme, that is in each of the globin chain, the iron where the oxygen is going to interact with. So pretty much uh, one hemoglobin, therefore, because of the four globin chain and four iron in it, can carry four oxygen molecules. And each association of oxygen and hemoglobin will form what you call a oxyhemoglobin or HbO2. And pretty much that's is exactly what's making our arterial blood bright red. Now, when oxygen is released, then hemoglobin turns reduced, and reduced hemoglobin is actually a little bit brownish or darker, and it's not bright. And that's why your venous blood is not as bright as your arterial blood. So, the loading and the unloading of oxygen is facilitated by a change in the shape of hemoglobin. As your oxygen binds into the hemoglobin changes in shape. When it changes in shape, it increases its affinity for oxygen. And then as oxygen is releases, the hemoglobin changes shape again, causes a decrease in the affinity for oxygen. Thus note that a fully saturated hemoglobin would have all four heme inside a globin, inside each of the globin chains, carrying oxygen. So 100% saturation means that every single iron in the heme group will have its oxygen paired up, associated with oxygen. Now, partially associated simply means when only one to about maybe three heme is actually being carried by the four globin chains. Let's say you have four globin chains, you have four heme and four iron inside it. If three out of four are the only ones that are associated with oxygen, and there's one heme or one iron that does not have any oxygen paired up with it, then you know that that's only a partially or a 75% um, um, oxygenated hemoglobin. So the rate of the loading and unloading of oxygen pretty much is regulated to ensure the adequate oxygen delivery to cells. And there are factors that are influencing hemoglobin saturation. First one is actually the pressure of oxygen, and other factors would include the temperature, blood pH, pressure of carbon dioxide, and the concentration of biphosphoglycerate. And biphosphoglycerate is one of the byproducts in a glycolysis reaction, and we'll discuss that later on and how it helps or how it affects the association of oxygen and hemoglobin. So let's start with oxygen. Oxygen heavily would influence the binding and the release of oxygen in hemoglobin, the pressure of oxygen, that is. And the percent of hemoglobin saturation can be plotted against the pressure of oxygen concentrations. Pretty much, I'm going to show you a graph. This is not linear, but it's actually an S shape, and is referred to as the oxygen hemoglobin association curve. Okay, and there you go, guys. There you go. And it's not really very visible, but you can actually look at it and revisit this in your textbook. Okay, pretty much it will help you. The association, the oxygen hemoglobin dissociation curve, which is this particular S-shaped curve, okay, will help you understand the properties of hemoglobin that affects oxygen binding in the lungs and the oxygen release in humans. Now, take note. Let's take opportunity to get this to understand this. This is your hemoglobin right here. Okay, let me get this. Uh, this is your hemoglobin. Right there is your hemoglobin. And this one here, this hemoglobin right here, has four oxygen. The red bullets are your oxygen. So you see that it is actually right here, 100%. It's actually saturated by 100%, which means all iron in the hemoglobin is paired up with oxygen. Right here, only three out of the four, okay, three out of the four iron is actually like filled up, and therefore you have 75% um, what do you call this, saturation. And right here you have only two out of the four, and so that's actually 50% saturation. And this one here is almost like impossible. You're not going to have this like 25% association. These are for people who are possibly going to die already. All right. So, in our normal thing, in our normal day-to-day thing, okay, when we're breathing, we hemoglobin is maximized up to about 100% saturation. Each time it goes to the lungs, it picks up all the oxygen and gets saturated 100%. The moment it's delivered into the tissues, it loses one of its oxygen only. So it's going to be about 75% saturated. Then it goes back to the lungs, okay? And when it goes back to the lungs, it picks up again that 25. So we on a normal day-to-day thing, we usually do not go down lower than 75% saturation. We lose for every one hemoglobin, we lose only one oxygen molecule, but we have millions of hemoglobin and we have millions of oxygen molecule. And therefore, a 25% loss will be just like breathing out already a good chunk of oxygen. And so let's take a look at the influence of what do you call this, the pressure of oxygen on hemoglobin saturation in the arterial blood. Okay, oxygen is 100 millimeters of mercury pressure and contains about 20 ml of oxygen if you're going to weigh it per 100 ml of blood, and that's actually like almost like 20% volume. Now, hemoglobin here, at this point, is actually 98% saturated. And further increases the pressure of oxygen as in deep breathing, okay, when you are deep breathing, will really not produce much. It produces minimal increase in oxygen binding. In the venous blood, where oxygen is about 40 millimeters of mercury pressure, which is really very low compared to the arterial blood, which is 100 millimeters of mercury pressure. These particular 40 millimeters of mercury pressure in the venous blood contains about 15% by volume of oxygen. Okay, so here your hemoglobin, just like what I mentioned to you in the previous slide, your hemoglobin is still, okay, even at 40 millimeters of mercury pressure, our hemoglobin is still 75% saturated. Now, this is actually very good because now we have what we call the venous reserve. The venous blood really have lost only like 25% oxygen. The oxygen remaining in the venous blood can still be used even if we get into an accident that we are not going to be breathing. Then the venous blood can actually still supply us several minutes of oxygen delivery to the brain so that the brain will not be damaged, and some of the other vital organs also, before our cells could get into a complete stop or shock. the venous reserve would pretty much continue on supplying the oxygen that is needed by the body in such instances. Okay, so the amount of oxygen carried by the hemoglobin depends on the pressure of oxygen available, okay, or the amount of oxygen available locally, like at that moment. This relationship would pretty much make sure that there's actual optimal oxygen pickup and delivery. Okay, so for instance, at sea level, there's actually like a lot of oxygen, okay, at sea level, and pretty much you can maintain your 98% saturation right here. But at high altitude, do you remember the saturation curve, which is at S? At high altitude, there's actually less oxygen, and therefore the lungs can only like achieve like 95% saturation. Okay, and when we are resting, okay, here is actually these are all arterial blood. Here is actually in the lower section you have the venous blood. In the resting tissues, the pressure of oxygen in the blood is about 40 millimeters and is 75 percent saturated. But for metabolically active tissues, for instance, during exercise, the partial pressure or the pressure of oxygen in the blood gets to be even lower. Okay, the hemoglobin is only 40% saturated, and therefore an additional 35% of oxygen has been unloaded for the tissue use. So right here, that's the reason why an athlete, or when we are active, we have the tendency to really breathe faster. We are in need of more oxygen. We feel that our body is in need of more oxygen because a lot of the oxygen that is in the blood is being unloaded for muscular action or activity use. So let's take a look at other factors that influence hemoglobin saturation. Um, Factors such as increase in temperature, increase in hydrogen ion concentration, or carbon dioxide, and the biphosphoglycerate can modify the structure of hemoglobin. Remember that the hemoglobin folding or change in shape of hemoglobin is the one that would affect or influence the release or the take up of oxygen, the hemoglobin's take up of oxygen from the blood. Now, an increase in temperature and carbon dioxide and BPG can modify the structure of hemoglobin and results in a decrease for hemoglobin's affinity for oxygen. And this really would occur in systemic arteries. It enhances the unloading of oxygen, causing a shift in the oxygen hemoglobin dissociation curve pretty much to the right. And decreases in these factors like temperature, hydrogen ion, or PCO2 and BPG can shift the curve to the left, which decreases oxygen unloading from the blood. Okay, so this is showing you how the shift is actually happening. You could take a look at the what do you call this? The unloading of oxygen at normal body temperature, which is the purple line right there. That is at normal body temperature. Okay, right there. That is the normal dissociation curve. Okay, the shift is going towards the right when the body temperature goes a little bit higher, right there. Okay, so then when it is actually like lower, when the body temperature is lower, then the shift is also going to be to the left. And in the same token, you have your the effect of carbon dioxide on the oxygen hemoglobin dissociation curve. It shifts to the right whenever your carbon dioxide is higher, okay? And that's actually an increase. And then a decrease in carbon dioxide will shift it to the left. So more on the influence of other factors. Biphosphoglycerate is produced by the red blood cell during the breakdown of glucose. Okay. And next week, we're going to be discussing glycolysis. When we get into the digestive system, we're going to be discussing glycolysis, our way of producing ATP, the use of sugar. Okay. So BPG is a byproduct of glycolysis. When BPG levels rise, okay, they rise when oxygen levels are low. So as your cell would metabolize glucose, they use really oxygen, okay, which causes an increase in the carbon dioxide and hydrogen ion concentration in the blood. Now, the declining pH, which is actually when you have more of the hydrogen ion, your pH would become more acidic, okay? And increasing uh, carbon dioxide will cause the oxyhemoglobin, the hemoglobin and oxygen bond to get weaker. Now, this is particularly called the Bohr effect, okay? Now, this Bohr effect or this effect would eventually lead to the unloading of oxygen where it is actually needed most. So, heat production in active tissues, okay, would directly and indirectly decrease the affinity for oxygen. It allows increased oxygen unloading to the active tissues. Okay, so the more active you get, okay, that will decrease the affinity for oxygen, and pretty much oxygen, because of decreased affinity, will be released out. Okay, it allows the unloading of oxygen to the tissues. Now, carbon dioxide transport. Now that you have at least we have gone through and finished the effect of these factors in the loading and unloading of oxygen. Let's take a look at carbon dioxide. Carbon dioxide is dissolved in the plasma, about 7 to 10% of it. Okay, or it could be about chemically bound to hemoglobin also, um, and forming a substance which is called carbaminohemoglobin. Now there is supposed to be an arrow going in that direction, right there. Okay, and pretty much 20% of the carbon dioxide is carbaminohemoglobin. And carbon dioxide can also be bound to the globin part of hemoglobin, and that's what you call carbaminohemoglobin. So carbon dioxide, when it is dissolved in the water, forms bicarbonate. About 70% will be forming bicarbonate. Now, the formation of this ion involves carbon dioxide combining with water, okay, which would quickly dissociate into the bicarbonate and hydrogen ion. So here, guys, you can see that you have carbon dioxide. That's carbon dioxide, right? This section here is carbon dioxide, okay, plus water. This will now give you carbonic acid, okay, H2CO3. Carbonic acid can dissociate into hydrogen ion and the bicarbonate ion, or the bicarbonate ion, there's an equilibrium going on here, can also dissociate back into the carbonic acid. So in the blood, the carbon dioxide that is dissolved in the blood is actually being used in the form of carbonic acid. And if you remember, when we were doing a discussion in the acid base, carbonic acid is a weak acid and it is a buffer. So our blood has a buffering system in the form of the carbon dioxide, which is in the form of carbon dioxide when it is actually dissolved in the blood. And It occurs primarily in red blood cells where the enzyme carbonic anhydrase, okay, in the presence of carbonic anhydrase, will reversibly and rapidly catalyze this particular interaction. In the systemic arteries, as a matter of fact, after bicarbonate is created, it quickly will diffuse from the red blood cell into the plasma. And the outrush of this bicarbonate ion from the red blood cell is balanced by chloride moving into the red blood cell from the plasma. So there's actually what you call an exchange. This is referred to as a chloride shift. And that, folks, is actually where you will find the chloride shift right there. Okay. Okay. Not only that part, this entire part right here is actually showing you the chloride shift. So, carbon dioxide in pulmonary capillaries. Uh, in pulmonary capillaries would have a reverse process or occurs in a reverse process. The bicarbonate moves into red blood cell while the chloride moves out of the red blood cell and back into the plasma. The bicarbonate binds with the hydrogen ion to form H2CO3, which is carbonic acid again. So H2CO3 is split by carbonic anhydrase again into carbon dioxide and water. That's exactly how carbon dioxide plays along with forming the weak buffer carbonic acid back and forth as carbon dioxide. And then when it reaches the lungs, it will diffuse out as alveoli, as gas, as a waste gas in the alveoli. Okay. So let's take a look at again another effect that was observed by a scientist, and he it was named after him. It was called the Haldane effect. Case amount of carbon dioxide transported is affected by how much carbon dioxide is actually available or the pressure of carbon dioxide present. The lower the PO2, not carbon dioxide, but the pressure of oxygen. The lower the pressure of oxygen and hemoglobin oxygen saturation, the more carbon dioxide can be carried in the blood. Okay, so that's actually probably very quite explanatory when you have the other one, which is actually the primary molecule that is being carried by your hemoglobin. If you will have lower oxygen around, then that's an opportunity for carbon dioxide to be carried in the blood. The more carbon dioxide can be carried in the blood. And reduced hemoglobin buffers the hydrogen ion and forms carbamino hemoglobin more easily. So this is actually where the uh, the reduction of hemoglobin happens faster when oxygen is actually low. The process will encourage carbon dioxide exchange at tissues and in the lungs. At the tissues, more carbon dioxide enters the blood. More oxygen would dissociate from hemoglobin. Remember this? This is actually what you call the Bohr's effect. And as um, oxyhemoglobin releases oxygen, it actually releases oxygen, it more readily forms bonds with carbon dioxide to form this carbamino hemoglobin. Okay, and this is actually just the big picture of what I have given to you about the Bohr effect, the chloride shift, and the Haldane effect. And please read on it. Okay, so let's take a look at the influence of carbon dioxide on blood pH. And you know that carbon dioxide, when it is in the water, will form carbonic acid. And therefore, you have your carbonic acid bicarbonate buffer system. Therefore, having said that, even if you know that this is an acid, still it is a buffer. It's a weak acid. It's a buffer, and it helps the blood resist a change in pH. Have you ever thought of, why, despite the fact that we probably will be like taking in a lot of something that is acidic and will be acidifying our blood doesn't really go very acidic. It's because we have the carbonic acid bicarbonate buffer. Among all the buffers, we still have other buffers in the blood. Okay. So when hydrogen ion concentration in the blood is in excess, okay, then your bicarbonates will form the H2CO3. That's actually the buffering effect. Now, if the hydrogen ion concentration begins to drop, okay, the carbonic acid would dissociate and it would release the hydrogen ion to even out the drop in the hydrogen ion. Now, the bicarbonate itself of the H2CO3 is considered our alkaline reserve. Now, changes in the way we are breathing, the deep, or rather the depth by which we are breathing, can actually affect blood pH. The slow, shallow breathing can cause an increase in carbon dioxide in the blood and will result in a drop in pH. That means your carbon dioxide, there's going to be shallow breathing, and therefore you're not releasing enough of the carbon dioxide. It mixes with the water portion of the blood. Then you will have high levels of uh, bicarbonate ion, and that will cause a drop in the pH because bicarbonate, the carbonic acid is still an acid. Rapid breathing, though, can cause a decrease in carbon dioxide level because now you're pushing a lot of blood into the lungs, and that would speed up the release of carbon dioxide, and more carbon dioxide is going to be released into the atmosphere. Changes in the ventilation can help adjust pH when disturbances are caused by metabolic factors. For instance, breathing itself play a major role in the acid-base balance of the body. Now let's take a look at hypoxia. Hypoxia, it's actually something that we feel when our blood oxygen level is low. That's actually what it means. And hypoxia is inadequate oxygen delivery to tissues and can cause cyanosis and is classified by cause. For instance, you have anemic hypoxia if you have too few red blood cells, or abnormal or too little hemoglobin. If you have a microcytic red blood cell, your hemoglobin is very small, or your red blood cell takes up less hemoglobin, then you can actually have anemia. You're probably anemic. Now, ischemic hypoxia is actually the impaired or blocked blood circulation. Histotoxic hypoxia, this is when cells are unable to use oxygen, as in metabolic poison such as cyanide. Okay, the cyanide will pretty much disable the cell's ability to metabolite, or rather to use oxygen itself. Hypoxemic hypoxia. This is abnormal ventilation. It's a pulmonary disease. Now, low levels of oxygen in the air can also be the cause. Carbon monoxide poisoning. This is especially from fire. Now, hemoglobin has greater affinity for carbon monoxide than oxygen. And therefore, instead of picking up oxygen, we pick up carbon monoxide. And carbon monoxide being replacing what do you call this, all of that space in the hemoglobin instead, that's actually meant for the oxygen, will deprive our tissues of the valuable oxygen because carbon monoxide is useless to our tissues. So here victims have headaches and can become flushed and eventually die because of hypoxia. Let's take a look at this, and I'm hoping that this is actually something that you can oh, I wonder.
Whether you're racing in a triathlon or doing something less strenuous, you need to breathe in oxygen to help you get energy. and breathe out carbon dioxide, a waste product. When you inhale, your diaphragm and rib muscles contract, increasing the volume of your lungs. When you exhale, these muscles relax, decreasing the volume of the lungs. When the lungs expand, air pressure in the lungs drops, causing air to flow into the lungs. When lung volume decreases, air pressure increases, causing air to flow out of the lungs. Air enters the nose or mouth, moves down the trachea, and goes into the two bronchi. Air moves down smaller and smaller bronchioles until it reaches a tiny sac, an alveolus. Each alveolus is surrounded by capillaries. Oxygen diffuses from the alveolus to the blood, and carbon dioxide diffuses from the blood to the alveolus. As blood flows through the capillary, it becomes rich in oxygen. In the blood, oxygen diffuses into a red blood cell and binds to hemoglobin, a protein made up of 4 subunits. One oxygen molecule can bind to each subunit. Oxygen-rich blood flows from the lungs to the heart. Which pumps this blood to capillaries all over the body. Here, we see oxygen diffusing from a capillary's red blood cells into a muscle cell. Oxygen is used by the cell's mitochondria to produce ATP during cellular respiration. Carbon dioxide is released. How does carbon dioxide leave the body? Carbon dioxide diffuses from cells into capillaries. Some carbon dioxide stays in the plasma, the liquid part of the blood. Most carbon dioxide, however, enters red blood cells. Some carbon dioxide binds to hemoglobin. The rest is converted to bicarbonate, which diffuses into the plasma. This oxygen-poor blood flows back to the heart, which pumps it to the lungs. There, carbon dioxide diffuses from the plasma into the alveolus. Bicarbonate enters red blood cells and is converted back to carbon dioxide. Carbon dioxide is also released from hemoglobin. Carbon dioxide diffuses out of the red blood cells, into the plasma, and into the alveolus. When you exhale, air flows out of your lungs. And that's how you release carbon dioxide, get oxygen, and keep on running.
So, let's move on with our control of respiration. I hope that video helped you understand the loading and unloading of both carbon dioxide and oxygen in the blood. So, how is respiration or how is our breathing controlled? Now, our rhythm, our respiratory rhythm, are regulated by the higher brain centers, the chemoreceptors, and other reflexes. Let's take a look at the neural mechanisms. Neural control would involve neurons in the reticular formation of the medulla and the pons. So let me change that into a laser pointer right there. Okay, that's where your medulla right here and the pons. Okay, and the medullary respiratory centers, which is clustered of neurons in 2 areas of the medulla, are the most important. These are your ventral respiratory group, or otherwise known as the VRG, and the dorsal respiratory group, which is otherwise known as the DRG. Okay, so this is your ventral respiratory group, which is located on the anterior side on the pons area. It contains the rhythm generators whose output drives your respiration. Meanwhile, your dorsal respiratory group integrates the peripheral sensory input and modifies the rhythms that are generated by your VRG. Okay? So, your ventral respiratory group, the rhythm generating and integrative center. Now, there are evidences recently that suggest that forced expiration may involve a separate group of neurons than just passive respiration. And this VRG consists of a group of neurons in the brainstem that extends from the spinal cord all the way to the pons medulla junction. So this one, the VRG, sets the eupna, which is actually the normal respiratory rate rhythm, 12 to about 15 breaths per minute. Its inspiratory neurons would excite the inspiratory muscle, okay, our muscle that makes us breathe in, via the phrenic nerve and the diaphragm and the intercostal nerves. The expiratory neurons would pretty much like inhibit your inspiratory. Uh, the expiratory neurons would inhibit the inspiratory neurons. Now the dorsal respiratory group, which is actually at the back, pretty much is a network of neurons that is just located there. It integrates input only of the peripheral stretch and chemoreceptors. There's not really much known, but exactly what the nature is of the dorsal respiratory group, except that it integrates input from chemoreceptors and brings it over to the VRG. Okay, so it's only like some sort of like a helper. The pontine centers. The pontine respiratory centers, which is actually this big thing right here, is actually neurons in this center would influence the activity of your ventral respiratory group. They act to smooth out transition between inspiration and expiration and vice versa. They transmit impulses to the VRG that modifies and fine-tune breathing rhythms during vocalization and sleep and exercise. Any lesion that would develop in this area of the brain would lead to our inability to breathe. Okay, and at this instant, patient will just have prolonged inspiration. We are unable to develop the correct rhythm. So, how is rhythm generated? Well, the origin of rhythm is really not fully understood. There is actually one hypothesis that we have a pacemaker neuron right there in the VRG, okay, and that controls the intrinsic rhythmicity of our breathing. But the most widely accepted hypothesis is actually nothing but just the reciprocal inhibition of two sets of interconnected pacemaker neurons in the medulla, and these are the ones that generate the rhythm. And each neuron set controls the other to ensure that there's actually a rhythm. So they're actually controlling each other. So let's take a look at how breathing rate and depth are influenced by some factors. Depth is determined by how actively respiratory center stimulates the respiratory muscles. Okay, the greater the stimulation, the greater the number of motor units that gets excited, and therefore it will increase the depth of inspiration. And rate, on the other hand, is determined by how long center is active or how long the inspiratory center is actually active. Both are modified by changing body demands. So your respiratory centers are affected by chemical factors, the influence of higher brain centers, pulmonary irritants, and inflation reflex, Ring-Bauer reflex. The chemical factors, most important of all factors that are affecting the depth and rate of inspiration, pretty much is the changing level of our gases, carbon dioxide, oxygen, and pH, most importantly. And the levels of these factors are sensed by central chemoreceptors, okay, that's located in the brainstem, and peripheral chemoreceptors that are found in the aortic arch and the carotid arteries. So the influence of carbon dioxide, the presence of carbon dioxide is very potent. It is the most potent and the most closely controlled. Although carbon dioxide level is actually very low in the atmosphere, we are actually producing carbon dioxide. And the carbon dioxide is actually, this gas is the most soluble in water among all the three gases that what we are inhaling in the air. So if the blood carbon dioxide level would rise because we are producing it, we are going to undergo what you call hypercapnia. It's a condition where carbon dioxide accumulates in the brain, in the joints, with water to become carbonic acid. The carbonic acid would dissociate, it would release the hydronium ion, it causes a drop in the pH, and acidity would increase. And increased hydrogen ion stimulates the chemoreceptors in the brainstem, which synapses with the respiratory regulatory centers. Now, respiratory centers increase depth and rate of breathing, which acts to lower the PCO2 of the blood and pH to normal levels. So, let's continue on. So, if blood level of carbon dioxide would decrease, the respiration becomes very slow and very shallow. Now, the word apnea refers to the stoppage of breathing, and this may occur when the carbon dioxide level drops abnormally low. Sometimes swimmers voluntarily would have to hyperventilate in order to enable them to hold their breath longer. Eventually, this causes a drop in the PCO2, which causes a delay in respiration, as carbon dioxide levels would need to build up back again, and can cause a dangerous drop in your oxygen level. Okay. So hyperventilation would increase depth and rate of breathing that exceeds body's need to remove carbon dioxide, and this could be caused by anxiety attacks itself, and would lead to decreased blood carbon dioxide level, and so we develop what you call a hypocapnia. It causes cerebral vasoconstriction and cerebral ischemia, resulting in dizziness and fainting. Now, early symptoms would include tingling and involuntary muscular spasm in hands and in face. The treatment for hypocapnia will be to breathe into a paper bag, which will increase carbon dioxide levels that's being inspired. So let's take a look at the influence of oxygen. We have peripheral chemoreceptors in our aortic and carotid bodies. These could sense the changes in oxygen levels. Declining oxygen levels normally has only slight effect on ventilation because of the huge reservoir of oxygen that's bound to hemoglobin. And that particular venous reserve is actually causing the slight effect only. Now, it requires substantial drop in PO2, which is about below millimeters of mercury pressure, in order to stimulate increased ventilation. Usually that will not happen, and that happens only whenever probably we're holding our breath. When When excited, the chemoreceptors can cause respiratory centers to increase ventilation. So, what are the factors affecting breathing rate or breathing rate and depth? Let's take a look at the influence of the pH, blood pH in the arteries. pH can modify respiratory rate and rhythm even if carbon dioxide and oxygen levels are normal. They're mediated by peripheral chemoreceptors. A decrease in pH may reflect carbon dioxide retention, accumulation of lactic acid, or excess ketone bodies. Respiratory system controls attempt to raise pH by increasing the respiratory rate and depth. That's actually the entire system itself. So let's take a look at the chemical factors. Okay, again, let's summarize it. Uh, rising carbon rising carbon dioxide levels are most powerful respiratory stimulant. That's actually always constantly being watched for. Normally, blood PO2 affects breathing only indirectly by influencing the peripheral chemoreceptor because of our venous reserve. The arterial PO2 fall When the arterial PO2 falls below 60 millimeters, then it becomes a major stimulus for respiration. But if it's a normal breathing, our blood oxygen level drops only to about 75% or 75 or which is actually above 60 millimeters of mercury pressure, and it's really not much of a concern yet. Changes in arterial pH could cause or resulting from CO2 retention or metabolic factor can act directly through peripheral chemoreceptors. So let's take a look at the influence of higher brain centers. Um, in the hypothalamus acts through the limbic system to modify the rate and depth of respiration. For example, when breath holding occurs uh, in anger or when we are gasping in pain, the change in band uh, in okay, let me say that again. Okay, uh, the hypothalamus acts through the limbic system to modify rate and depth of respiration. Example of this is when we're holding breath, okay, that occurs in anger or gasping with pain. Because the hypothalamus is actually the emotional part of the limbic system and part of the emotional brain. And remember that it is actually the one that would pretty much like affect our bodily activity whenever we are emotional. Okay, and when we hold our breath, whenever we're angry or whenever we're gasping in pain, that pretty much is actually modifying the rate and depth of our respiration. And then uh, change in body temperature would change also the rate. Now, cortical controls, and that's actually in the cortex. Okay, it directs signal from the cerebral motor cortex that bypass the medullary control. Example: when you are breathing voluntary breathing, voluntary breath holding, at least until the brainstem reinstates breathing when blood carbon dioxide becomes critical. Okay, so when you're holding your breath, okay, um, un- until the brainstem itself reinstates breathing when carbon dioxide becomes critical. So you cannot really hold your breath long enough. You can only hold your breath at some time until the carbon dioxide level becomes critical and we are going to be forced to breathe. That's actually what it is. Okay, take a look at some pulmonary irritant reflexes. Now, gut receptors in the bronchioles. They respond to irritants such as dust, accumulated mucus, or nauseous fumes. Okay, our receptors communicate with respiratory centers via the vagal nerve afferents. And these irritants promote reflexive constriction of air passages. And some irritants, the same irritant would trigger cough in trachea or bronchi or sneeze in the nasal cavity. The inflation reflex, also known as the Herring-Bauer reflex, pretty much happens when stretch receptors in the cover of the lungs, the pleura of the lungs and airways, are stimulated by lung inflation. So whenever we are breathing, whenever we're taking in air as much as we can only take in as much air as we can, you know. Whenever the stretch receptors feel that we are overstretching, okay, these stretch receptors send inhibitory signals to the medullary receptor centers to end the inhalation and would allow exhalation. They may act as a protective response more than a normal regulatory mechanism. It's protecting our lungs from exploding, I guess. All right. Okay, so here's actually a good way of reviewing the neural and chemical influences of the brain using a picture. Okay, make sure that you see this. Now, let's take a look at some respiratory adjustments when we're breathing. Exercise. During exercise, adjustments are actually geared to both the intensity and the duration, okay, of breathing itself. And this must be made in order that we can take in oxygen um, to the needed muscles in the body while we're actually doing this action, and release carbon dioxide that is being produced whenever our muscles are also metabolically engaged. Hyper, hyperpnea. It is increased ventilation in response to metabolic needs. So your breathing rate is going to increase, sometimes 10 to 20 fold. So ventilation abruptly would increase, it gradually and abruptly, then reaches a steady state. When exercise stops, there is a small abrupt decline also in ventilation, followed by a gradual decrease, okay, in your PO2, and your carbon dioxide and pH remain surprisingly constant during our exercise. That means that's actually the aim of homeostasis. We increase our breathing rate in order that these particular levels of these molecules would stay the same, because you don't want too much carbon dioxide to accumulate. You don't want to lose much of the oxygen. Okay, so our ventilation is the one that would uh, need to adjust in order to maintain them. So abrupt increase in ventilation that occurs as exercise begins involves three neural factors. First one is psychological stimulus. This is actually our in anticipation. This is what happens in anticipation of the exercise. The simultaneous cortical motor activation of skeletal muscles and respiratory centers also is the next reason. And then the excitatory impulse to the respiratory centers from proprioceptors in moving muscles and tendons and joints. The gradual increase and plateau of respiration respiration reflect is actually caused by increased rate of carbon dioxide delivery to the lungs. So ventilation declines suddenly as your exercise ends, because the three neural factors are actually going to shut off. The gradual decline to the baseline is due to decline in carbon dioxide flow after the exercise ends. Exercise leads to anaerobic respiration and the formation of lactic acid. The lack of oxygen in the muscle is not from poor respiratory function, really, but rather from insufficient cardiac output or skeletal muscle inability to increase the oxygen uptake. Now, quick travel to altitudes, like going up in mountains above 2,400 meters or 8,000 feet, may trigger symptoms of acute mountain sickness. If you're not really used to it, you are definitely going to experience this. The atmospheric pressure and oxygen level are lower at higher elevations. Therefore, you can have symptoms like oxygen, shortness of breath, nausea, dizziness. In severe cases, lethal cerebral and pulmonary edema may occur. That's why it is not advisable really just to travel up in a high mountain, most especially if you have COPD. It would be best if you can actually like acclimatize yourself and go slowly. And therefore, you get into different areas and stay in different areas for a few hours or days and then go at a higher elevation. It is really difficult, most especially for people with a COPD. Acclimatization refers to respiratory and hematopoietic adjustments that are made with long-term move to high altitude, and that's exactly what I'm talking about, where chemoreceptors become more responsive to the carbon dioxide and oxygen declines. And the substantial decline in PO2 directly stimulates the peripheral chemoreceptors and results in increased in-minute ventilation that stabilizes a few days, okay, about 2 to 3 liters per minute higher than sea level. A high altitude condition always results in lower than normal hemoglobin saturation levels, and this is due to less availability of oxygen, and therefore results in a decline in blood oxygen and stimulates the kidney to accelerate the production of EPO. And EPO is erythropoietin, and is what is this? This is a hormone um, that is involved in stimulating the bone marrow or the hemocytoblast into producing more red blood cell. So there's going to be increase in red blood cell numbers to provide long-term compensation for the decline in oxygen. So we're done here, guys. We are, this is the end, but it's not the end of the chapter. There are still lung diseases, and I'm holding you responsible in self-studying the virus lung diseases in your textbook. It is going to be part of the test in the lecture.